Hello, everyone, and thank you for joining us for our presentation, MPC Research MPC 579, Where the Sidewalk Ends, and MPC 615, a LiDAR-based approach to quantitatively assessing streetscapes. Today's presentation is brought to you by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University and is a partnership with the four state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Mountain Plains Consortium, which includes 8 universities in Colorado, North Dakota, South Dakota, Utah, and Wyoming. Our speakers today are Dr. Wes Marshall. He is a professor of civil engineering and affiliate faculty in urban and regional planning at the University of Colorado, Denver, director of the Colorado University Denver Transportation Research Center, and co-director of the Active Communities Transportation Research Group, ACT. He is a professional engineer and focuses on transportation teaching and research dedicated to creating a more sustainable and resilient built environment, particularly in terms of road safety, active transportation, and transit. Joining him today is Nick Coppola. He is a civil engineering lecturer at the University of Colorado, Denver, and a fiber optic GIS administrator at the Colorado Department of Transportation. For 6 years, he has been involved in research, teaching, and assisting in transportation and GIS coursework for the University of Colorado, Denver. And having worked prior in the private sector on transportation, natural resources, cultural resources, and renewable energy products. With that, I will go ahead and mute myself and turn the presentation over to you, Wes.
Thanks, Chris. Thanks for having us. Welcome, everyone. Again, I'm Wes Marshall. I'm a professor of civil engineering at University of Colorado, Denver. I appreciate you taking the time to join myself and Nick today, even though I'm guessing you're probably as sick of Zoom calls as I am. Nevertheless, we wanted to talk about a few of our sort of recent research projects. To give it some context, I wanted to start by talking about some of our current transportation problems. So I think if you ask most transportation engineers to talk about our current situation, they might start with something like this. Like you see these ASCE report cards about our crumbling infrastructure and bridges or our failing transit systems. This grade was a little bit surprising to me because I've heard that on the Northeast Corridor, we're still using rail infrastructure that was put in place when Abraham Lincoln was president. But nevertheless, related to the infrastructure crisis is the fact that oftentimes we're being choked by traffic congestion. In fact, solving traffic congestion is inevitably one of the key national transportation priorities. Other issues worth mentioning, air quality is a big one, which has a direct impact on public health. And these are just the long-term health problems, and many are immediate. And a lot of these problems aren't half a world away like you see in Delhi in those pictures, but this is the Suncor refinery right not far from where I am, right in Commerce City. I'm not sure what that orange plume of smoke is, but I know I don't want to live or work that close to it. And last August, Denver, for one day, we had the worst air quality in the world. Like this is a list of those cities. And when it comes to things like public health and transportation, we sort of neglect road safety for some reason. We sort of gloss over that. But clearly dying on the roads is not good for your health. Over 46,000 people died on U.S. roads last year, which on average is like 125 people per day. And I can give you all sorts of shocking statistics on road safety like this one. Since 9/11, more Americans have died on the roads than both world wars combined. Or this one, every day around the world, more people die every day on the roads than in the 9/11 attacks. But we sort of treat these deaths as the cost of doing business as opposed to a public health issue that it is. So engineers will lay out a lot of these problems, like the traffic congestion and the infrastructure, and they say, well, how are we going to fix all this? Like one, give us some money. That's always a good start. The second is always technology. We sort of feel like things like autonomous cars or hyperloops are going to fix everything. When I say everything, I sort of mean everything. Like you see here, it's going to help keep our air clean, get rid of parking, eliminate traffic. Everything's going to be safe. We're not even going to need street signs. We can expand our sidewalks. Here's a funny kids book I found about this autonomous future of ours, where we can convert our parking garages into these amazing mixed-use buildings and reminisce back to a time when cars had to park there. Why don't we need parking? Well, the autonomous cars are going to be busy apparently cleaning our streets, watering our plants, and changing light bulbs. So for me, that's sort of the context here. I have a hard time getting excited about spending trillions of dollars on all that technology when we can't even get our damn sidewalks right. Here's a picture from Denver of a 2-foot rolled curb type sidewalk on a major street where a lot of people walk on, and we can't even fit 2 people side by side on a sidewalk like this. And those were great sidewalk compared to a lot of places. Here's an example where the sidewalks are just completely missing. And to me, it should be embarrassing for a major city. Like, these pictures are from Denver, and to see curb ramps that lead to nowhere or sidewalks that just end. And we can't even be bothered to put a decent sidewalk next to a bus stop, even along a major arterial. Or, here there's at least a sidewalk, but it's not what I would expect for this corridor, which 22,000 people a day use the buses on this street. This is a picture that Nick took of this terrible sidewalk leading to a light rail station that we've invested billions of dollars into. And we don't give people a great way to get there by foot. But that is better than a lot of what I see. Here's another bus stop where it's missing. In big picture, I think it's easy to forget that real people use these places. And I took this picture. This is less than a mile from where I'm standing right now in downtown Denver. And when we don't provide this sort of fundamental infrastructure, we force real people into dangerous situations. Like, here's a wheelchair user that can't fit on one of those narrow sidewalks. And I see this time and time again. And when, for someone like me that sort of thinks about transportation as I sort of bike and go around the city, it always seemed to be a bigger problem in some neighborhoods than others. So particularly those that are minority, or those where income seem to be lower. So that is sort of one of the research questions we asked in part of this work, and to see if those perceptions are true. And that's one of the things Nick will be talking about shortly when he starts up his presentation. Before we get to that, one of the other things we investigated was how municipalities handle asset management when it comes to sidewalks. So one of my master's students, Peyton Gibson, we interviewed 16 different cities, and we tried to collect data understand how they collect roadway data and how they use that data. So when we asked about roadways, so we didn't ask about sidewalks at all at first. We found out that they're collecting these amazing road data. They're doing it on a very regular basis, and they're putting it into these high-end software packages. If there's a pothole, they're going to be out there in at most a day or two to fix it. After we asked those road questions, we ended up asking the exact same questions about sidewalks. And almost every time we heard a similar thing, like, well, it's complicated. What we found out is that most cities have no idea where their sidewalks are. They systematically go about trying to not collect that data. And it's funny because when I first moved to Denver in 2009, I found this sidewalk polygon layer on Denver's OpenGIS website. Interestingly, it was dated back to 2004. Every other data set that they were working with was updated on a regular basis. For some reason, this one wasn't. When I asked somebody what the city is, like, what's going on? I was told that the city's lawyers told them that they couldn't update this because if they knew there was a problem, they'd be liable. So it's not like we couldn't collect this data. It's that we were sticking our heads in the sand or maybe down a manhole. But that doesn't work. What we found out is that cities were getting sued regardless of their purposely trying to ignore this issue. And they were losing these lawsuits. And I think cities were now beginning to realize that pretending not to know there's a problem is not going to work. So at the same time, when Nick was sort of beginning his PhD dissertation type work, we were realizing that a lot of cities were collecting what is called planimetric data based on high resolution imagery. And some of these cities aren't even doing it for the infrastructure side. They're doing it so they can send me a bill about how much impervious area I have in my land. This is a bill I got in the mail last fall, where basically I'm charged by the amount of impervious area that they create from that planimetric data. But this data can also be used to quantify sidewalks. So regardless of the underlying intent of the data, it's a huge opportunity. And, I think it was sort of fortunate timing to have Nick looking for a dissertation around that same time because he was sort of the perfect student to take on this challenge. He just had gotten his master's in GIS, and that sort of skill set was really needed to do this. So as he was working towards his PhD in transportation engineering, I think you'll see when Nick presents how invaluable that skill set was. So Nick will tell you a little bit more about some of the existing research as well, but I think one of the initially shocking things for us was how little research there is out there on sidewalks. And of the research that is out there, most of it will look at a very limited area, so like a single neighborhood, or the sidewalk data will be, compromised, so to say. Like they'll collect the sidewalk data from the inside of a moving car, like using a clipboard. Or it was actually pretty wild to see what some of the researchers were doing to even collect sidewalk data. This is rapidly changing though. So the data that we are able to collect for this infrastructure is only going to get better and better. So in sort of the second MPC project that we're talking about today, another PhD student of mine, Yaniv Golembeck, he analyzed LiDAR data basically to see what we could see. So LiDAR stands for light detection and ranging, which is a remote sensing technology that uses pulse lasers to measure range. And with that, the U.S. government has started what was called the 3DEP program, 3D elevation program. They were collecting a national LiDAR database. And at the beginning, it was called QL2, so quality level 2. So Yaniv wanted to sort of figure out what we could see with this. Could we start seeing things like sidewalks or other street furniture, things like that? At first, though, with that quality level 2, all we could really see were the trees and the building. So here you can see a group of trees embedded within this LiDAR point cloud. But we could measure those trees. And with this, we could get things like the density of the trees or how much tree canopy there was, and we could start connecting it to, maybe road safety and start understanding whether the clear zone type convention is actually leading to safer streets or not. But we weren't yet coming close to seeing sidewalks. We could start seeing maybe traffic light features, things like that. The next paper that Yaniv and I did looked at quality level 2 data, quality level 1 data, so QL1, which you see on the right here. It's about 8 times denser of a point cloud than the QL2 data that you see on the left. Now, not only can we make out the street trees and the buildings, but we could legitimately extract and statistically quantify things like fences or walls or any vegetation, light posts, traffic lights, power poles, power lines, street signs, and started getting into street furniture, benches and things like that. Sidewalks, though, were still a little bit elusive with this. But in the third paper that Yaniv and I did, and this is sort of the overview of his almost whole dissertation, was the mobile LiDAR. So you can see here at the bottom, which is collecting thousands of points per square meter compared to sort of the 8 per square meter with the QL1. Now we can see pretty much everything, including sidewalks. Here you see us identifying a traffic signal, stop sign, a pole, a fire hydrant. And as you can see here, we're starting to get into the sidewalk stuff. So it's not just for us whether the sidewalk exists or not, or even the width. I mean, that sort of the basis we can get with the planimetric data that Nick will talk about. But with our next MPC project that we're working on now, we're looking to extract ADA information, so the Americans with Disability Act. So such as being able to see sort of the 1/4-inch lip on a sidewalk, which we can't get with the planimetric data, but maybe we're going to be able to get in the next iteration of this work here. And this is some data we collected with a LiDAR mobile backpack and just sort of walking around a building on campus here. And that took about 15 minutes to collect that data. So that's what we're sort of working on next. But for now, like I said, I have a hard time hearing people sort of pine over autonomous cars and hyperloops when we're still failing at our most basic infrastructure, sidewalks. So that's what we're sort of trying to do with this research, is take a closer look at the humble sidewalk and to start to think about how we do better. In some cases, it's pretty obvious how we can do better. Well, actually, in a lot of cases, it's pretty obvious how we can do better. And it's disappointing. And sad or almost embarrassing, really, some of the things that we're putting out there. And even when we think we did well, we often leave people with an obstacle course to get around. And here's an example that I took this picture biking to work not that long ago, where a wheelchair user was sort of forced into the street because the sidewalk was sort of cluttered with obstructions. Luckily, in this case, she had a protected bike lane to sort of safely roll in, but in a lot of streets, we don't. So it's easy to sort of laugh about pictures like this, but at the same time, this is real, this is important, and because most situations don't provide sort of any decent alternative to that. So we can do better. And it is complicated. Sidewalks are only one part of it, because we can place a decent sidewalk along a terrible arterial like this here in Denver. And despite the fact that it borders a public school, we can't be bothered to drop the speed limit even during school zone time. So even in a location like this, on a DOT-controlled arterial street, where students have lost their lives as pedestrians, we have to realize that this is, I think, more than an asset management issue. So in the second half of the presentation, Nick is going to tell you about how we measured the sidewalks and planometric data and how we sort of use that to look at issues like equality and getting at things like equity. So Nick, like I said, he's a PhD graduate of ours. He now teaches a GIS and transportation course for us. And as Chris said at the beginning, he works at Colorado DOT.
So circling back to kind of at the heart of what Dr. Marshall was even talking about is that even back in 1990, the federal government was willing to be very forthright and acknowledge the fact that walking is considered a forgotten mode of transportation. Now, since then, we've seen a concerted effort across the country where pedestrian plans and master pedestrian plans are being put out by different cities nationwide. So, this is a great start. But the unfortunate thing is that we're still seeing that this is not working. We're still unable to attend to the issues that we're seeing for pedestrians across the United States. And a really good example that we found was with Milwaukee's pedestrian plan. They're very frank about it, which I loved, in the way that they state that, number one, they have a lack of funding when it comes to their infrastructure, for pedestrian infrastructure. And two, it points out sort of potentially part of the reason for that is a lack of data for making decisions on this. They lack data on their sidewalks, curb ramps, so on and so forth. Now, going beyond just government, and we're looking at federal government, local, state, town, we're seeing in the academic literature as well that they're still pointing out that there's a lack of geospatial data when it comes to sidewalks and pedestrian infrastructure. But on top of the lack of data, we're seeing that there's a lack of analysis being done and a lack of literature being posted on this. So in comes our research. We're looking to help fill this gap, fill this void, and we're going to use some of these advances in spatial data to help answer some of these questions. So the first thing we did was we wanted to take a look at planometric data and the provision of sidewalk infrastructure in cities. So when we say planometric data, what exactly do we mean? So this is a really good example, and Dr. Marshall had already sort of mentioned this. So let's dig a little bit deeper. So planometric data would be taking aerial imagery and then creating a two-dimensional representation of infrastructure on the ground. So in this image, you can see, obviously, they are essentially tracing the outline of buildings, which you can see in yellow, outlines of roadways in black, and sidewalks in green. So when we took a look at what the prior literature was giving us, we were finding that when they had sidewalk data, they were very limited. They were very constrained. So you'd see like a small section of the city, maybe a couple streets, maybe a neighborhood. And when they wanted to expand that and they wanted to do research for the entire city, they would end up using roadways. And as we all know, just because a roadway exists doesn't mean that a sidewalk exists. So obviously, there's a lot of room for improvement here. So the way that we started this was we just went all in and we looked at essentially every single city, 769 cities that were posted by the U.S. Census. And this was by no means an easy task. It took a lot of detective work. So what we had to do was we had to look through different agencies. We had to check cities, we had to check counties, we had to check region councils of government. There was no particular place where you could find this data. It was all over the place. To make it even more difficult, the amount of information that was presented on these data sets was limited at best. A lot of times there would be absolutely nothing, which led to us making lots of phone calls, lots of emails. We had to dig through the data sets themselves and look at all the features to see what is it that we're actually getting here. Now, part of what made that such a trying task is the fact that it didn't always look like this, where you got this perfect data set, and this wasn't even perfect by any means, but at least you knew there were sidewalks, right? What we were finding was that there was different naming conventions, different titles that were given to these data sets where sidewalks were hidden. Sometimes it was under a data set called paved areas. Sometimes it would be buried even deeper, where you'd have to find a data set called structure, and within that there was a data set called impervious surface, and then within that is where you would find sidewalks. So it was not an easy task to even find this data. In the end, we were able to find 24 cities that had viable data that we could work with. And with these 24 cities, now we have planimetric data where we can take what the prior literature was giving us, where we were only looking at a small section of a city, and now we can expand that. Now we can cover the entire city. So to take a deeper dive into what this looks like, this would be an example of planimetric data. So you have your buildings, your sidewalks, and your roads, similar to what we showed in that earlier picture. And what we had to do was we had to normalize that data. We had to find a way to make it the same for every city. So what we did was we would extract the sidewalks and the roads, and then from there we would use parcel data sets so that we could limit it to being within the public right-of-way. And this is based on conversations we had with multiple cities across the United States. This is their approach, using the parcel data set to help normalize that data and to limit it to within the public right-of-way. So what we wanted to look for, we wanted to keep it, pretty straightforward. Sidewalk availability. So if you have sidewalks on both sides of the road, you have 100% availability. And if you only had sidewalks on half, then you have 50%. So keeping it pretty simple. Next, we look at sidewalk average width. So if you had a sidewalk polygon that had 4 foot and 2 foot of equal length, you'd have 3 foot average width. We also looked for sidewalk minimum width. So minimum width pretty much speaks for itself. You want to find that pinch point. What is the narrowest section of that sidewalk polygon within that data set? Here it would be 2 foot. Now the sidewalk width is helpful, but we need to compare that up against something. So what we did was we took a look at the Americans with Disabilities Act, which is a standard. So the ADA is a law. So this is sort of like the gold standard of the 3 foot mark. The ADA has proposed that they want to move that to 4 foot. This has not been enacted into law yet. So we took a look at the 3 foot and the 4 foot to start with. And then beyond that, we looked at other agencies and their guidelines, such as AASHTO, FHWA, and that essentially ended up breaking it up in 3, 4, 5, and 6 foot thresholds for what we were looking at. In addition to the width, we also took a look at the land coverage. So by land coverage, what we mean is the relative comparison of sidewalk area of coverage within the right-of-way compared to roadway land coverage within the right-of-way. So this is an example of some of the results that we found. So on the left, you'll see Peoria, where there's a high overall sidewalk width, which is very easily noticeable based on the symbology shown here in the colors, as opposed to Cedar Rapids, where you can see a significant difference in sidewalk availability, sidewalk width. And then on the other side, when we looked at sidewalk availability, this is very easily noticeable. You can see a considerable number of sidewalks in Corvallis compared to in Lynchburg. So what does this actually look like in terms of what the results are telling us? What it looks like is that we have a deficiency in sidewalk availability based on those cities that we took a look at. And more specifically, what that comes down to is about 50% sidewalk availability. So 50% sidewalk availability, when you think about that, would mean you have a sidewalk on one side of the road, but not on the other. And that can be a pretty dangerous scenario, especially for people with disabilities who may have a harder time getting around. We also found that just over 10% of these sidewalks failed to meet that ADA compliance at 3 feet. Now, looking at sidewalks similar to what Dr. Marshall was showing earlier, these are other sidewalks in Denver. And I would agree, this is kind of embarrassing. You see a sidewalk that's not even 3 foot wide, and yet on the right-hand side, you can see cars are even allowed to park and narrow that even more. In some scenarios, it's not even walkable for a group of people who have full range of motion, full ability. And then lastly, when we looked at land coverage, you can see the juggernaut here. The roadway takes over basically. So 88% in that relative comparison, 88% of the land coverage was the roadway and about 12% were sidewalks. But kind of coming back to the main point here is what we found is that the traditional methods of having to go to the field and to collect this data manually, which would take an insane amount of time, almost not even be feasible when you think about cities like Boston or New York City. What we found is that we can supplement this. We can work with that, and now we can make use of data. We can make use of advances in spatial data, and we can contribute to this. We're capable of doing that, and that's what this first component of the research shows. So we took it a step further from that, and this was sort of a sidebar from the paper presented, but we took a look at static obstructions as well. And the reason for that, and the reason why I want to point this out, is because spatial data has a tendency to make sidewalks look like this. They're perfect. You have these great polygons with nothing in the way. Everything looks great, but the reality is this is typically what we come across in urban areas. There's always going to be something in the way. It's not always going to be perfect like that. So we took a look at Cambridge, Massachusetts. We found with a little more research and a little more digging, Cambridge had some excellent data. And taking a closer look at what their data looked like, as an example, this is what planimetric data would look like for sidewalks before including obstructions. So this is kind of what you would typically get. Almost looks perfect, right? But when you start adding static obstructions, this is a completely different scenario. Your sidewalk doesn't look anything like it did originally. So let's take an even closer look at what that looks like as an example with one of these sidewalk polygons that's being collected. So if that sidewalk polygon shows that you have 5 feet of width, that sounds great, correct? So as a city or a state or a county, if you're looking at this, you're thinking, this is fantastic. We have 5 foot width here, easily accessible. But then when you include static obstructions, all of a sudden that all goes away. Now you realize that you only have 2 feet around that obstruction for somebody to get around, and that isn't accessible. That's not ADA accessible. So we've realized that static obstructions bring a completely different ballgame to this. When we say static obstructions, we looked at 18 different static obstructions based on the data available to us. So for example, you have trees, benches, you have lighting, you have garbage cans, fixed garbage cans that are in place. And in total, there were over 30,000 of these features throughout Cambridge. So the first thing we did was we wanted to identify what would the maximum width be for a pedestrian going around obstacles. And in this case, it would be 5 feet. Then we took a look and we said, what would be the minimum width? What's that pinch point if they actually wanted to navigate this sidewalk with these obstructions? And what we found was that goes from 5 foot to realistically being 2 foot. So that's a considerable difference of what it would be without obstructions versus when you incorporate those obstructions. So the results show us that the number of compliant sidewalks can be cut nearly in half, which is considerably different. So if we didn't have static obstructions, that's what the maps on the left will show you. So when we're looking at 3 foot, you would have 78% compliance. And then when we did introduce static obstructions, which is this image on the right, it's only 51%. That's a 34% difference. And we went through this for each one of those benchmarks of 3 foot, 4 foot, 5 foot, and 6 foot. So at 4 foot, without introducing obstructions, it was 59% compliance. And with obstructions, 31% compliance, 48% difference. At 5 foot, we went from 36% down to 18%, which is essentially 49%, just about 50% difference. And then at 6 foot, we went from 17% compliance down to 11%. So before moving on to this next section, it's important, and I want to at least point out the fact that we wanted to point that out because data sets don't typically provide that level of detail for planimetric data. That was an anomaly in a sense, but it is definitely something that tunes you into the fact that even though planimetric data helps us to move to that next stage and is helpful giving us more information from the data available, we could still do better, and that shows reasons why we still need to do better. So the next paper we looked at was the unequal distribution of sidewalk infrastructure across 16 U.S. cities. So typically in cities, this looks a lot like some of the pictures we've already seen. This is what a quote-unquote sidewalk would look like. It's really not a sidewalk. They don't exist. Or they're too narrow, or they lead to absolutely nothing, maybe one building. So the question we had was, which populations are most impacted by this? So it's important to take a step back and realize what we're aiming for here is research and analysis on the equality of the distribution. So how equally are sidewalks being distributed throughout a city? And by understanding how equally those sidewalks are being distributed, it gives us more insight to equity and understanding how that can impact different demographics. What we also found is this is becoming more of interest, I guess you could say. It's been pointed out in recent literature, academic literature, that cities are more interested in this. So to be more specific, if you look at the Boulder pedestrian plan, they come right out and state essentially they're looking to be more equitable and inclusive when it comes to their pedestrian plan. But it's difficult because we're still seeing the fact that agencies lack documentation on this infrastructure. So how do they make these decisions? So that's where we come in once again. We're looking to help fill that void in the literature. So we took a look at 16 different cities. And the first thing we looked at was sidewalk availability. So what we found was with those 16 cities, there were 3 different groups essentially that we found. When we took a look at the results for individual cities, they ended up showing tendencies to group together. So that first group that we found were these cities that show greater sidewalk availability and higher median household income. In another group, what we found was greater sidewalk availability and lower median household income. And then lastly, we found a small group where there was no apparent trend that showed either of those. So when we took a look at sidewalk width, what we found was wider average width was often associated in the cities we looked at with lower income and greater non-white block groups. When we looked at wider minimum width, we found the same thing. Lower income and greater non-white block groups. So overall, what we found is that these advances in technology have shown promise and capability. They can give us that information to help us expand. We can use this data. The data is available, and we can use this to expand our knowledge from a larger scale across an entire city to understand more about what our sidewalks look like. It's important to remember that the purpose of this is we want to understand it for the people. Sidewalks are for people to be able to get from point A to point B, to enjoy themselves, to go out, to be able to have a bite to eat together, to get to and from work, or just to go out for their own leisure. But this is the realities of what our sidewalks actually look like. And part of that is, as we've noticed, it's pointed out that there's a lack of data and a lack of information that can be gained. So this is the result, or this is part of what ends up coming from that when we can't identify where the problems actually exist. And we need to understand how to make this more equitable. We need to understand how to make this for people so that we can enjoy what is a foundational component of our transportation system. We need to be able to allow children to be able to get to and from school or just to enjoy themselves without having to be worried or fear their safety. And same thing for the parents. We need to make it a vibrant place again. And with that, I'd like to say thank you very much. I think we ended a little bit early, which is probably good. And with that, I'll turn it back over to you, Chris.
We do have a couple questions, so let's go ahead and just get through those. The first question that popped in was about the sidewalks. So what about sidewalks where there is no roadway? Sidewalks may connect two streets where there is no through auto traffic. So did you address any of that, or do you have any feedback on that?
Yeah, we were able to use this technique to collect the sidewalk data for where there weren't roadways, such as through parks. For the sake of the metrics that Nick was showing, though, we treated those separately, though.
Okay. And then did you address driveway aprons that may create excessive cross slope and generally reduce a pedestrian's sense of comfort?
So,
go ahead, Dr. Marshall.
Yeah, and in the next project, we're going to be using the mobile LiDAR and to get to that level of detail. For what Nick did, I think, Nick, you can explain this. The trick was sort of making sure that we knew that it was a passable sidewalk, because the apron, when you get the impervious area, it looked like the sidewalk sort of expands up the driveway. So we're trying to cut it off at the right of way, as Nick was describing.
Yeah, so I'm sure all of you noticed that as we went through the progression of our research, we went from looking at 769 cities in the beginning, and then we had 24 cities in the beginning, or I should say after that we found 16 cities that we could research. Well, we continued to dig. We didn't just leave it at that after we found those 16 cities that we could do research with. We dug deeper, and that ties into what Dr. Marshall was just saying. We found that just because sidewalks are available and just because they quote unquote cover the city, you still have to dig even deeper. You have to call the city to find out, when was that data collected? Is it being collected every year? Are they doing it just for sections of the city? How does that work? It becomes more complicated the deeper that you dig. And part of that is, what do you call a sidewalk, quote unquote? And that gets into this discussion here about driveway aprons. So we attended to that in the later research that we were doing to make sure that those driveway aprons were being accounted for. Some cities, it would just be considered part of the sidewalk with their data set for sidewalks. Others, it was considered separate. So it becomes really hairy, and you really have to do your research on it to make sure that you understand, what do they mean by a sidewalk? Because the definition of what a sidewalk is in the geospatial data in cities and counties across the United States are all different. And I think that's one of the big areas that I think needs attention more than anything. There's no standard. It seems like roadways have more standards and management in their geospatial data that you can rely upon than what we found with the sidewalk data.
And then David Keene did ask another thing on width. And David, you may want to unmute and maybe ask this last question or make the statement that you're trying to make. But he said width may be associated with roadway classification for vehicles. It also may reflect the era of initial development. So if you want to maybe clarify exactly what you were stating there, feel free to go ahead.
And looking at our data, I think it's been more the latter than the former.
Okay.
So era development is sort of a big thing. And even in terms of quality of sidewalks, you see some of the older neighborhoods where contractors had to sort of stamp their name from 50, 60 years old. Those are still in great shape today, but newer ones from the 70s and 80s have fallen apart completely. And I think it's a reflection of sort of our priorities at the time and sort of how we thought about transportation and infrastructure and sidewalks. And So yeah, roadway classification probably does play some role, but it feels like the latter when sort of neighborhoods were developed.
And then with the mobile LiDAR, is the collection strategy to use a wheeled device such as LiDAR mounted on a Segway? Think Bellingham used this, and so just kind of clarifying that.
So we're going to use a backpack one. So there's a little device that you put on the backpack. It kind of hangs above you. And we're actually going to compare that with a lot of places are trying to collect this data from LiDAR from a car in the street. And we're going to try to see, well, where and when that works well versus where that doesn't. Because if the sidewalk is sort of offset and there's sort of green space in between, if there's elevation change, if there's parked cars, like you would think that the street-based LiDAR would not work as well. So one of the comparisons we're going to be doing is sort of how much better the doing it from the sidewalk is and when you could theoretically use the car-based version and get away with it.
Okay. Any other questions out there? And while you guys are thinking about that, I'm actually going to do a quick little search here because, and actually, Wes, maybe you know, was there some additional research done that kind of tied with some of the urban area type research that you did to tie to more of a rural setting? I think there was some additional, maybe some research done on that. Are you familiar with that?
You know, when Nick did his sort of comprehensive look for who and had this sort of sidewalk data, I don't think we found too many, you know, what would be considered rural areas that were collecting this. Nick, do you have any?
Yeah, I was going to say that's where the benefit of when you had the county who is in charge of this data collection would come in. So once again, as we dug a little bit deeper into researching where this planimetric data was available, we were finding that the county level data was helpful in the sense that if you did want to look at some rural areas, that would be available because at times they would just do a blanket, basically data collection for the entire county. And in situations like that, you could pull that data for rural areas. It just wasn't as prevalent as working with urban areas, and the other part of it being that our initial focus was on urban areas. So we sort of stuck to that, and that's where you are more likely to find it. I think part of that has to do with funding as well. The Denver Regional Council of Governments, which is sort of what started it all, Dr. Marshall had a slide in there for Dr. Cog. A lot of it is based, meaning the data collection, is based on buy-in. So you would have to have these different townships or cities within the Regional Council of Governments area of coverage to take part in it. They would also provide funding to want to have data collected for their area. So that's another part of it too. I'm sure funding also has part to do with the lack of data in the rural areas.
Okay. In bigger picture, I think it would be important to start doing this kind of work in rural areas too. Because if you look at sort of where pedestrian fatalities are happening, there's a sort of shocking number happening in rural locations too. So, a lot of those two-way rural roads, people are sort of forced to walk upon, and they're dark, and you often can't see around the corner, and there aren't sidewalks on them. So, given sort of relatively lower exposure, pedestrian exposure in those places, there's a relatively high number of deaths in that. So I think this would be worth expanding and looking at other contexts.
I agree, and I will say part of Upper Great Plains Transportation Institute, some of their initiatives, I know they're looking at accessibility, meaning accessibility for pedestrians and bicyclists in the rural areas, including the tribal reservations. I know there's so at least some data being collected in that, so that might be something to kind of look at too, and I do know we do have a team working on that. There was a question on specific LiDAR manufacturer type that you're planning to use.
It's tricky because the cost of it is so high. We have to sort of put it out to bid. We can't sort of just pick the one we want. So we're going through that process now. Like, even though we feel like there's one we might prefer, we can't just easily go in that direction. So that's been, we'll see what happens.
Okay, and then with the storage, data storage, I know this is a big thing with UAS as well as LiDAR. So DOT data storage becoming an issue. Any suggestions or comments regarding how to store, update, or even maintain those data sets?
That's a good question. And Nick, do you have insight from doing some of the work you're doing now at CDOT?
Yeah, as I say, I can give a little bit of insight. I think the DOTs, and of course I can only speak for working with the state of Colorado, to just kind of keep it really basic. I think there's already an influx of data that they're having a hard time managing and being able to analyze to turn that data into information to begin with. So LiDAR is one of them that I'm aware of. It's a money and manpower thing too. I mean, we within the DOT already have so many components of transportation, the system, the infrastructure that we need to do geospatial data management and analysis for that already stretches us thin. And then when you start adding more through ITS devices with traffic counters and license plate readers and all this other stuff, it only makes it more challenging on an already strained group, I guess you could say, both funding wise and personnel wise. So I wouldn't say that there's necessarily an answer to how that's going to be fixed, but it's definitely something we're well aware of. So yeah, that doesn't really give much of an answer, but I think it just maybe gives more insight to just that you're correct in the sense that it is something we have to figure out how to do, because I feel like they're collecting it and there's only so much we can do with it with the money and manpower we have.
A suggestion in the chat was don't store the raw data, store the derived data that changes in conditions.
Yeah, that's a good point. One thing I forgot to mention before too, I mentioned how we're going to be comparing the mobile LiDAR on the backpack to based in the car. We're also going to be trying to collect the data with the new iPhone. The new iPhone can collect LiDAR data, and we're going to hopefully see if it's possible to sort of crowdsource sidewalk infrastructure data and sort of see what ADA type, can we get that 1/4 inch threshold, or is it more of a 1/2 inch? So we're actually, Nick and myself and another student, Chris, are going out next week or the week after. I'm going to try it with a few of these different devices and sort of compare and contrast what ADA issues we can come across with the different levels. And, is an iPhone actually a viable approach to doing some of this for places that, maybe not have the wherewithal to get one of the expensive, better devices?
I mean, they're measuring the sometimes ride roughness with iPhones and with smartphones now. So, I don't see why some of that wouldn't come into play. So with the crowdsourcing, how did you maintain QA/AC procedures?
Well, we'll see. We haven't collected the data yet and see. Yeah, we don't really quite know how easy it's going to be to geolocate the data and how, like, getting data from two different iPhones, how we can even mesh them together in the first place. If we look at the Denver Streets Partnership, that used to be Walk Denver, they had a website where people could sort of upload sidewalk issues, and it was, an online map. People could take pictures, upload comments, and it was really a step above what most places were doing. And it was, you couldn't really control the quality very well, but for a municipality that's trying to figure out where to maybe start, it might give them places to go look at. And I think that's what we're trying to do here, is sort of help cities prioritize this sort of infrastructure. And, maybe we can't get it sort of to the exact level that we are doing with roads where we're hiring a contractor. But part of that is we're not putting in the same amount of funding to getting the sidewalk data as roadways. But if we are trying to crowdsource it, hopefully we can get it to a point where we can, figure out where to start. Like, how can we use this to give a city some direction and where they might want to put some resources and some time and actually have somebody go out to the field. And one of the papers that Nick did as well, where we used some data from Streetlight to look at where people are actually walking. Because it's one thing to have a crappy sidewalk in an industrial area, and it's another thing to have a crappy sidewalk where there's a high level of pedestrian use, or even where there's a high level of cars making very short trips, like a mile or less. So we use the combination of sort of demand from the streetlight data with our sidewalk data to try to prioritize, where we could start looking to fix the infrastructure. Because the city of Denver had a guy that was going from neighborhood to neighborhood, and when you look at how long it was going to take him, it was like 200 years before you could collect all the sidewalk data. And what we did in like a few weeks, we're able to sort of use the planimetric data in combination and say, if you send somebody out to like these 3 neighborhoods, like you have a good sense of what you can do and where you can start. So I think that is the direction we're heading with a lot of this stuff.
Very good. Thank you for that. All right. Well, with that, thank you for attending today's TLN event. We appreciate your time, participation, and attention. Wes and Nick, thank you so much for sharing this research concepts and practices, and best of luck in your future research as well. This is a very valuable, safe, and important project to work on. So thank you for spending the time to do that and sharing your information back with us. Sincerely hope you enjoyed and gained some new knowledge from today's presentation. I encourage you to visit our website at translearning.org for upcoming learning opportunities, as well as to access the learning management system. And again, if you see something out there that is of interest, please share that with your peers so they have the opportunity to sit in as well. Again, thank you guys so much for your time and attention today. Have a fantastic week. Be safe and don't forget to be awesome. Take care, everyone.